All right, welcome. Today, we're going to add some seriously powerful new tools to your calculus toolkit. The derivatives of all those trigonometric functions. You ever wonder how you'd calculate the rate of change of a wave or, any kind of oscillation? Well, this is exactly where it all starts. Let's jump right in. So here's our game plan. First, we'll get into the why, the whole rhythm behind these derivatives. Then, we'll get down to business with the 6 core rules you just got to know. After that, we'll see how to use them with the product and quotient rules, and we'll wrap it all up with the one key takeaway that's going to make this all stick.
First up, the rhythm of calculus. Look, before we just start memorizing a bunch of formulas, it's so important to understand the concept behind them. So why do these derivatives even matter so much?
Well, think about it. Sine and cosine waves, they describe basically everything that's cyclical. We're talking sound waves, AC current, planetary orbits, you name it. And since these functions repeat in a perfect cycle, it only makes sense that their derivatives, their rates of change, have to be cyclical too. This is a huge link between pure math and real-world physics and engineering.
Okay, now for the main event, the 6 fundamental derivatives. These are the absolute must-have tools for your calculus kit. You're going to want to commit these to memory.
Just take a look at this table. On the left, you've got your primary functions. The derivative of sine is cosine. Simple enough. Tangent gives you secant squared, and secant gives you secant times tangent. Now, look over at the right side, at all the co-functions. Cosine, cotangent, and cosecant. Do you see the pattern here? The derivative of cosine is negative sine. The derivative of cotangent is negative cosecant squared. And cosecant, negative cosecant cotangent. Every single co-function has a negative derivative. If you remember that, you're halfway there.
All right, so we've got the basic rules down, but what's the point if we don't use them, right? Let's see how we can combine our new trig derivatives with something we already know, the product rule, to solve some more interesting problems.
Just a super quick refresher on the product rule. The derivative of two things multiplied together, f times g, is f prime g plus fg prime. Got it? Good. Let's use it. So let's tackle y equals x squared times sine x. Step 1, we just identify our two functions. Let's call f x squared and g sine x. Easy enough. Step 2, find their derivatives. F prime is 2x, and we just learned that g prime, the derivative of sine, is cos x. Now for step 3, we just plug everything into that product rule formula. And there's our answer. Y prime equals 2x sine x plus x squared cos x.
Next up, the quotient rule. And trust me, you're going to want to stick around for this one. This example starts out looking like a total mess, but the way it simplifies in the end, it is just so satisfying.
And here's the rule itself. You probably remember the little rhyme for this one, right? Low d high minus high d low over the square of what's below. We're going to use this for the function sine x over 1 plus cos x.
Okay, so applying the rule, our low is 1 plus cos x, and our high is sine x. So low d high is 1 plus cos x times cos x, and high d low is sine x times negative sine x. We put it together, and yeah, I know, that numerator looks like a handful, but just watch what happens next.
When we expand that numerator out, we get cos x plus cos squared x plus sine squared x. Now, stop. Take a good look at that. Does anything there look familiar? Something that's just begging to be simplified? It's that cos squared x plus sine squared x part, isn't it?
And there it is, the good old Pythagorean identity. This is the magic key that unlocks the whole problem. You know this one. Sine squared plus cosine squared always equals 1.
So we can just swap out that whole cos squared x plus sine squared x chunk for a simple 1. That gives us cos x plus 1 in the numerator. And look at that. We have a 1 plus cos x in the denominator squared. So one of them cancels out, leaving us with this beautifully clean final answer, 1 over 1 plus cos x. How cool is that? All that complexity just collapsed.
Okay, we've gone through a lot today, so let's boil it all down. If you forget everything else from this explainer, please remember this one key idea.
Here it is, the most important takeaway. All co-functions, that's cosine, cotangent, and cosecant, they all have negative derivatives. This one simple pattern literally cuts the amount of stuff you have to memorize in half. It's the most effective shortcut you're gonna find, I promise.
And that's a wrap.
You now have the fundamental tools to analyze the rate of change for any cyclical motion you can think of. So what's it going to be? The oscillation of a guitar string, the voltage in an electrical circuit. The power is in your hands now. Thanks for watching.